let's take two charges, point charges, let it be Q1 and another charge be plus Q2, and if they are separated by a distance R, they experience a force. This force depends upon the nature of the charges. If they are both same charges, plus and plus, so they experience a repulsive force. The force is away from it. So repulsive force. It's the repulsive force. So this is the direction of the force. So this force can be written as the force on the charge 2 by 1, and it is a vector quantity. So therefore, you must write an arrow mark above the force. Similarly, the charge Q1 is also experiences a force, but in opposite direction, and this force is represented as the force on the charge 1 by the charge 2, and it is also a vector quantity, and its direction is represented by so towards the left side, F12. This Coulomb's law is also called as the inverse square law. It's also called as inverse square law. Coulomb's law is called as inverse square law. What is the statement of this? What is the statement? The inverse law says that, inverse Coulomb's law states that, or just Coulomb's law states that the force attraction or repulsion, the force of attraction or repulsion between the 2 point charges is directly proportional to the magnitude of their charges. And inversely proportional to the square of the distance between them. That's why this law is also called as the inverse square law. This law is also called as the inverse square law. What is the mathematical the form of the inverse square law? We can measure the force between the two charges. Magnitude of the force between the two charges is a constant K into Q1 into Q2, only magnitude, divided by the square of the distance between them. Yes. In SI units, this force has to be measured in newtons, and charges have to be measured in coulomb, and if R is measured in meters, that means the distance between the charges, if they are measured in meters, then the constant K is given by 1 by 4 pi epsilon naught 1 by 4 by epsilon naught, where epsilon naught is called permittivity, vacuum permittivity, or trick permittivity of vacuum. Yes. So in SI units, the whole K value, the 1 by 4 epsilon naught value is found to be 9 into 10 to the power of 9. It's 9 into 10 to the power of 9. But it is found that here opposite charges, say plus Q1 and minus Q1, get attracted. The force is towards themselves, is attracted. This is, yes. Oppositely charged bodies attract. If they have different signs, one is plus, one is minus, they are attracted. If they have same charges, like one is minus Q1, another one is minus Q2, so the two charges are same charges, they get repelled. Get repelled. It is found that this Coulomb's law is similar to the Newton's law of gravitation. But gravitational forces are much weaker than the electrostatic forces. And gravitational forces are always attractive. But electrostatic forces may be either attractive or repulsive. Suppose if you keep the charges in other mediums, let's keep a charge Q1 and Q2 in a different mediums other than air or vacuum. So in different medium. Then the force between them is given by 1 by 4 pi. Instead of epsilon naught, you should write one epsilon r into epsilon naught, and Q1, Q2 r square. Here epsilon r is a dimensionless quantity. It's called as relative permittivity, relative electric permittivity. Of the medium. Different medium have different epsilon r values, relative permittivity of the medium. So sometimes the permittivity of the medium, the relative permittivity of the medium is represented as epsilon, which is nothing but relative permittivity and permittivity of the free space. Therefore, in any other medium, the force between the two charges is given by 4 pi epsilon Q1 by Q2 divided by r square. Suppose if you keep same charges Q1 and Q in different medium with same distances, then the ratio of the force is found to be inverse proportional to the epsilon r, as rest all constants. Therefore, if you calculate the ratio of the force of attraction or repulsion in air divided by in any medium, you will get same 1 by epsilon naught 1 into Q2 divided by square and 1 by 4 pi epsilon naught, 1 by 4 pi epsilon into epsilon r into epsilon naught. Same charges Q1, Q2 divided by r square. After dividing, everything get cancels. 1 by 4 pi epsilon, 1 by 4 pi epsilon naught, Q1 by Q2 by r square, Q1 by Q2 by r square. The remaining is just 1 divided by 1 by epsilon r. So that means the force of attraction or repulsion in the air divided by the force of attraction or repulsion in a different medium other than air, is given by just relative permittivity. It's a relative permittivity. If you know the relative permittivity, then the force of attraction or repulsion between the charges in air divided by relative permittivity gives the force of attraction or repulsion between the same charges in a different medium. What are the limitations of Coulomb's law? In which case Coulomb's law cannot be applied? Coulomb's law can be applied only for point charges. The charges must be point charges. Or charges may be residing on a spherical metal spheres, or charges may reside on a spherical sphere. Charges must not overlap. That means charges should have a clearly they are separated. There exists some distance between the charges. If the two charges lays one on the other, then we can't apply the Coulomb's law. So charges must not overlap. The next one is charges must be stationary. We can't apply the Coulomb's law to the moving charges. Charges must be stationary. Yes. So this is about the Coulomb's law. Then, what do you write? The definition of the Coulomb's law. According to Coulomb's law, the statement of the Coulomb's law. The Coulomb's law states that the force of attraction or repulsion between the two charges kept in a medium separated through some distance is found to be directly proportional to the product of their charges and inversely proportional to the square of the distance between them. On combining, we can say that the force of attraction or repulsion between the charged particles